So, welcome to a new lecture on flexibility matrix method of analysis. Today, we are going to discuss about indeterminate structures, solving the indeterminate structure using flexibility method. Comparing it with a determinate structure, the difference is that there is a multiple steps to be done. You have to repeat the process two times to find out the answer. That is, first we will define the system coordinates for external load and find the matrix. Then after which we will apply the redundant forces and then find the force transformation matrix. That's the difference. So let's see, the question is given, a continuous beam is given. We can clearly see it is an indeterminate beam or a flexibility matrix, also called as force method of analysis. Our main unknowns are forces. Main unknowns are forces, and it is also called as redundancy or degree of static indeterminacy. So find out, we are not interested in horizontal loads, and so horizontal load is removed, and degree of static indeterminacy is number of reactions minus number of equations of equilibrium. Equations of equilibrium are sigma fx is ignored, and sigma fy and sigma m will exist. Two equilibrium equations, and how many support reactions are there? One, two, 3, and 4. 4 support reactions. Hence, 4 minus 2 equal to 2 is a degree of static indeterminacy. That means there are two unknown forces which cannot be solved using equilibrium equation. So we have to go for compactability condition. So these two forces or this static indeterminacy actually indicates a number of system coordinates. So there are two system coordinates actually here, two force coordinates. So fixed end moment is my next step. Fixed end moment, apply the condition, find out the values. UD separate span, AB span, WL square by 12 is the formula. Substituting, I get the values. We have solved the same question using direct stiffness method as well. So there also the first initial steps are same. Fixed end moment is calculated. And for this case, the load for concentrated load, the span is 5 meter. So formula is WL by 8, and a clockwise is taken as negative, so minus 20 exists. So MFBC and MFCB is calculated. And the next step is equivalent joint load. Condition of equivalent joint load we have already discussed. That is, equivalent joint load is nothing but the applied load that may be a UDL. It may be applied throughout the span. So we are converting that load into some external load that's been applied onto the joint. Because by matrix method, we are only focusing on the load that's been applied onto joint. We don't consider the load that's been applied on the span. So convert the UDL load into a equivalent joint load, the load that's been applied onto the joint. So that is nothing but the fixed end moment being reversed, because fixed end moment is a load. Actually, it's a load or a moment that resists the applied load. That is opposite to the direction of applied load acting onto the two supports. So I convert that into an equivalent joint load acting on the support by changing its direction. So I reverse the direction. This is my fixed end moment. Resultant fixed end moment 113 and 20 acting down a clockwise direction. I change its direction. I get the equivalent joint load as 113 in anti-clockwise and 20 in anti-clockwise directions. Fourth step is system coordinate. I defined, that is system coordinate 1 and 2 in clockwise direction, and check it with the equivalent joint load. That is, equivalent joint loads are anti-clockwise. So I define the load matrix as minus in both the cases of minus 113, because it is opposite to the first system coordinate, minus 20 because it is opposite to the second system coordinate. Next, element coordinate split into two beams, two elements, that is element 1 and element 2. Find the element matrix, that is L by 6CI, 2 minus 1 minus 1, 2 is the general formula. Apply the length L value as well as EI value. L is 10 meter, EI value is 3 for the first case, and in the second case, L is a 10 itself, but EI value is 1. Here, EI value is 3. Applying and finally adding up, I get flexibility matrix, element flexibility matrix. It's a 4 by 4 matrix. Now, force transformation matrix, apply unit force at first system coordinate. So, R1 equal to 1, that is a moment, M equal to 1, I have applied. Find out the BMD. So any section I take, it is one itself. So here one. Here this side there exists no bending moment because the load is applied only here. So it will take its direction backward only. So B11 is -1 because it is anti-clockwise. How did I draw that BMD like that? This will produce a clockwise and in order to oppose that anti-clockwise. So this will come and an anti-clockwise direction is being produced. B11 is equal to -1. B21 equal to B21 is actually 1, that is acting clockwise direction. Moment is being applied. So B21 is 1. And applying unit force at a second coordinate R2 equal to 1, I get it as V12 is equal to -1, here 1, -1, and then 1. This is my final matrix, BR matrix. This is for determinate condition, external load. The extra additional step in the indeterminate problem is that you have to find the force transformation matrix for a redundant force Bx. So two redundant forces x1 and x2, no doubt in that, because we have already calculated the degree of static indeterminacy as 2. Two additional forces, this 2 will act as a two additional support reactions. So I consider it as two external loads x1 and x2, and then apply unit load at x1 and then calculate the BMD. I apply x1 equal to 1, find out the BMD. This will go like this and the beam will try to opposite it like this. Right, at this load, it is 1 into 10 moment clockwise direction. So I drew the bending moment diagram downwards. Here 10, here 0. So my B11 is 10 clockwise positive, B21 is 0, B31 0, B41 0. Similarly, apply unit load at 2, x2 equal to 1. The bending moment value is 20. The x1 is applied, it will try to make the beam upwards. In order to oppose this bending moment, a clockwise moment is developed, that is 20 into 1. So 20 is acting clockwise downwards, hence my bending moment diagram is being shown downwards with a clockwise sign 20 and then writing the values. Here at a 10 meter, you will have bending moment value as 10, 10. So 20 minus 10, 10 and 0 will be my Bx value. Now the formulas are, you have to study this formula, Bxx equal to Bx transpose dot F dot Bx. This is my formula. X is there, so this both will become X. XR is there. First X represents Bx transpose. Second R trans represents the last BR. That's the only difference. And finally, X is equal to, that is redundant force equal to minus of Fxx inverse dot Fxr dot R, this into and load matrix with a minus sign and an inverse is being taken. You have to study this formula. And finally, element forces is BR dot capital letter R plus BX dot X. X we have found out from this step. Then final end moment, element force Q plus fixed end moment we will add that. So let's see. Fxx is equal to Bx transpose dot F dot Bx. So Bx is this one. Substitute in calculator, find the value of Fxx. Then Fxr, Bx transpose is this one. Here we go for Br. F remains the same, calculating, we get Fxr. Then x value minus of Fxx inverse dot Fxr dot R. So you will get the redundant value. Now element force Br dot capital letter R plus Bx dot X. Substituting these values Br and load matrix Bx, and then now we found x value that we substitute find, and totally we will get a q value. This all have to be done in calculator so that you can easily find out the values. Then finally, q plus fixed end moment. This is fixed end moment we already calculated. Adding both these, we will get the final end moment. So let's draw the bending moment diagram. The red line indicates the final end moments we calculated now. That is 174 minus sign. We have studied this in sign conversion. Sign conversion in our first chapter in slope deflection method. At the left end, if you have a negative value, then it should be drawn above the baseline, and hence I drew it above the baseline. And if you have a positive value in the right direction, that is this point, it should be drawn above the baseline. And if you have a negative value in the right end, that is this one, It should be drawn above the baseline and hence it occurs here. It is 0. This is my final end moments. And then we are superimposing the fixed, simply supported beam condition. That means what happens in a real structure is that we are converting the bending moment of a simply supported beam to a fixed end condition. So there is a redistribution of moment occurring. Redistribution of moments at the support. That's what happens. That's why the bending moment diagram of a simply supported beam is actually converted to something else, or it's been opposed by the fixed end moments, and the resultant bending moment diagram will be the actual bending moment diagram of the structure. That's why the final end moments are cancelled out by the simply supported bending moment that is being shown in that is shown here. That is this arc and this triangular portion. This is due to a simply supported beam condition, right? There is UDL condition. We have WL square by 8, and for a center point load, we have the formula WL by 4 that's been shown here. Superimposing the area shaded becomes our final bending moment diagram.